electrolysis is running these spontaneous reactions backwards. So we're going to use electric current to drive a non-spontaneous reaction instead of getting electrical current from a spontaneous reaction. And the process is called electrolysis. So H2 gas plus O2 gas will make water. That is a spontaneous chemical reaction. It's used in that fuel cell. It will produce electrical current. But by supplying electrical current, we can cause the reverse reaction to occur. We can take water and break it down into hydrogen and oxygen gases. So one idea they're working on is a solar-powered electrolytic cell where you can use solar power to generate electricity and use that to generate hydrogen from water. And then you use the hydrogen to power the fuel cell. So here we have a battery, an external source of electrons, and we've got water in here, and there needs to be some type of soluble salt because pure water doesn't conduct electricity. And so we're passing electric current through this, and we're going to get oxygen bubbles at the anode and hydrogen bubbles at the cathode. And you can collect these gases and measure the relative amounts, and we see that we get twice as much hydrogen as oxygen, which makes sense when we think about the composition of water, right? There's 2 hydrogens for every oxygen. So you're going to generate twice as much hydrogen gas as oxygen gas. You can actually do a small version of this at home with a 9-volt battery and a cup of water. If you use distilled water, nothing's going to happen. But if you use tap water, you'll start to see little bubbles form at the cathode and the anode of the battery. So at one, those are hydrogen bubbles. At the other, there are oxygen bubbles. If you wanted to go faster, you can stir a little bit of salt in there to make the water more conductive. And so you can generate hydrogen and oxygen gas. And in theory, you could separate them and then recombine them and have a nice little explosion or something, but it's actually much harder said than done. Any questions? So other uses. We can use electrolysis to take metal oxides, which are naturally occurring, they're in the soil all over the place, and produce pure metal from them. So sodium metal is an example of this. We can take molten sodium chloride, so table salt. If you heat it to a high enough temperature, it will melt and become a liquid. You can't do that at home. It's really, really high temperature. But from that molten sodium chloride, which does conduct electricity, we can create or produce sodium metal. We can also use this to put metals onto other metals. It's called plating, electroplating. So you can put silver plating on a less expensive metal and have things that look like they're solid silver. So long, long time ago, people used to have silverware, and it was actually made of silver. It was solid silver. Very expensive, very valuable. People would steal spoons, right? Because just even as one spoon is like, ooh, that's going to get you something. Beautiful, but very expensive. And so with silver plating, you could make the forks and the spoons out of another kind of metal that's much cheaper, and then electroplate silver on the outside. So it has a thin layer of silver on the outside. It's going to look like real silverware. But you can tell the difference because it's not as heavy. The problem with silverware is the silver oxidizes, and so it tarnishes. And so you're always having to polish the silver. And every time you polish the silver, you remove a little bit of silver from the outside. And so with the silver-plated utensils, you're going to wear through that silver coating eventually. But this is how you could do something like that. You can have, here's your silver electrode, and here's the thing that you're plating the silver onto. And, this is going to be some sort of solution with electrolytes in it. And we're going to pull electrons out of the silver, which will create silver ions. And then the electrons are going to go through the battery, and they're going to be pushed into this object here. So here are a bunch of electrons waiting for somewhere to go. So the silver comes over here, takes an electron, and then it's elemental silver again, and so it just stays there. At the beginning of this chapter, we looked at zinc and copper, and how if you put a zinc strip into a copper solution, this black kind of crusty stuff forms on it, and that's copper depositing on the zinc strip. That's not how you want your silver to look, right? So you have to do it just the right way to get it to plate on there and be nice and smooth and shiny. So this is that cell we looked at the beginning with zinc and copper. And we have a spontaneous reaction that will generate current, generate a potential of 1.1 volts. In the electrolytic cell, what we're doing is we're forcing the electrons to go in the reverse direction. And so electrons are coming in here, and the zinc is becoming solid zinc ions, and here the copper is becoming copper ions. So it's backwards. So the anode and the cathode get switched. So some of these things you need to know. In all electrochemical cells, oxidation occurs at the anode, reduction occurs at the cathode. Reduction at the cathode, red cat. And oxidation and anode both start with a vowel. That's how I remember that. In a voltaic cell, the anode is the source of the electrons. The anode is negative. Oops. The anode is negative, like anions are negative. The cathode draws the electrons. The cathode is positive, like cations are positive. Electrons will flow from the anode to the cathode. They're repelled by the negative charge of the anode, and they're attracted by the positive charge of the cathode. So those are things you might need to know on an exam. In an electrolytic cell, things are backwards. And we're just going to leave it at that. We're not going to read that because we want to keep this clear in our minds. Okay, which statement is true for both electrolytic and voltaic cells? The cell spontaneously produces a positive voltage. Is that true for both kinds? No. It's true for a voltaic cell. Those are the kinds we talked about that generate current, right? They're spontaneous reactions. In an electrolytic cell, the reaction is not spontaneous, and we're forcing it to happen. So an electrolytic cell does not produce a positive voltage. So this one's not correct. Oops. That one's not correct. Electrons flow from the anode to the cathode. I don't know about you, but I don't really want to think about that one. It's kind of confusing, right? So let's see if the last one's a little easier. Oxidation occurs at the cathode. Okay, from what we talked about on the previous slide, where we were talking about voltaic cells, does oxidation happen at the cathode? No. Red cat, right? Reduction happens at the cathode. So this is not true for a voltaic cell. To answer this question, we don't need to know if it's true for an electrolytic cell. It's not true for both of them. So we can just eliminate that guide. Electrons do flow from the anode to the cathode. Predicting electrolysis products. So again, electrolysis, we are applying a voltage, we're forcing electrons to flow. If we do this in a pure molten salt like sodium chloride, we've got two things. We've got an anion and a cation. The anion is going to get oxidized and the cation is going to get reduced. So the example given is sodium chloride. Chlorine is already reduced, can't be further reduced, it'll get oxidized. Sodium is already oxidized, it can't be oxidized anymore, so it's going to get reduced. So here we have our molten sodium chloride, and we're forcing electrons through this, and we're creating sodium, elemental sodium. If there's more than one cation in that molten salt, like if we have sodium chloride and potassium chloride, then we have to look at which cation is more easily reduced. Those standard cell values don't apply to molten salts. The numbers are not the same. Those are for aqueous solutions at standard conditions. But the relative ordering is the same. So if we look at the reduction potentials for sodium and for potassium, sodium is negative 2.71, potassium is negative 2.92. This is less negative. This is easier to occur. So the sodium will be reduced first in preference to the potassium. There might be a couple homework questions on this. I'm not going to put this on the exam. If there's more than one anion, then you're looking at which one of those is more easily oxidized. So here we have oxidation half reactions. So the textbook's always going to give you the reduction potential, even if you're doing the oxidation. What makes more sense to me is if we're going to reverse the equation, then we're going to change the sign. And so the thing with the more positive voltage is going to be easier. And so here, bromide would oxidize rather than chloride if we had sodium bromide and sodium chloride. Again, could show up on a homework question, not going to be on an exam. In aqueous solutions, things become a little more complicated because water can be electrolyzed. So water can be oxidized to oxygen and reduced to hydrogen. It's not the water that's being oxidized and reduced, it's the oxygen and the hydrogen. When we combine these potentials, we see, well, what would that number be? 1.23 plus 0.83. It'd be negative 2.06 volts under standard conditions. But in pure water at room temperature, the conditions are not standard. So for pure water at room temperature, you need 1.23 volts to electrolyze water. So a 9-volt battery, 9 volts, plenty to electrolyze water. Pure water doesn't conduct But if you add an electrolyte, then you can get electrolysis to occur. So we can have electrolysis of the water in the aqueous solution. So we have to consider that compared to the other things that are in there. So if we have a sodium iodide solution, well, we can have oxygen getting oxidized, or we can have the iodide being oxidized. So aqueous solution, not standard, right? E for that is negative 0.82. We can have standard conditions for the iodide. 1 molar iodide would be negative 0.54 volts. So here, the iodide is easier to oxidize. It's less negative. Here we're looking at the reductions. We can have hydrogen in water being reduced to hydrogen gas, or sodium ions being reduced to sodium. And here, it's easier for the hydrogens to be reduced than the sodium. So you cannot get sodium from the electrolysis of an aqueous solution of sodium iodide or sodium chloride, because the water's going to be reduced instead of the sodium. There's an illustration of that. This is aqueous, not a molten salt. And so the iodide is getting oxidized at the anode, and over here, the sodium is not getting reduced. It's the hydrogen in the water that's getting reduced. And as if this doesn't sound complicated already, the other thing we have to think about is overvoltage. Many non-spontaneous reactions need more voltage than they should to get going. And water is one of those things. So water, in theory, you should be able to electrolyze it with 0.82 volts, but because of the overpotential, it's closer to 1.4 volts. And so this reminds me of Gibbs free energy, where the Gibbs free energy is the maximum amount of work that you could get out of this reaction, right? Do you ever get the maximum? No, you don't. And so here, when we're going backwards, this is the minimum needed to get it to go. But it's going to take more, because it's always more energy put in and less energy taken out. Stoichiometry of electrolysis. This is something that will be on the exam. So we can think of electrons as reactants in the electrolytic cell, and they have a stoichiometric relationship to the other reactants and products. So if we're plating copper, going from Cu2 plus to copper solid, you're coating a spoon, not sure why you'd want to do that, but whatever. There's a relationship here of stoichiometry. There's 2 moles of electrons for every 1 mole of copper ion, 2 moles of electrons for every 1 mole of solid copper that gets deposited. So we can measure the quantity of electrons by measuring the charge. We can't measure their mass. We could measure the mass of the copper, but we can't measure the mass of the electrons. We can figure out the number of moles of electrons, though, from the total charge that flowed, and that's going to depend on the magnitude of the charge, the magnitude of the current, and how long it flowed. So 1 amp of current is 1 coulomb per second. So if we have a current, say, of 2 amps, 2 coulombs per second, and we run that for 2 seconds, that means we have 4 coulombs of charge. And then we have the Faraday constant that relates coulombs to moles of electrons. So silver plating uses the reaction of Ag plus electron to Ag. How many moles of electrons must pass through an electrolytic cell in order to plate 3 moles of silver? This is a good exam question too. 3. And we got all these hard questions, and then some of them are just so easy that makes them hard because you think it couldn't be just that. 1 mole of electrons for every mole of silver. If we want 3 moles of silver, we need 3 moles of electrons to go through there. So there might be a question like this on the next exam. Not the one today, of course. So we can plate silver according to this half reaction, and this is asking how much time in minutes would it take to plate 12 grams of silver using a current of 3 amps. You can look through the table of equations, and you're not going to find an equation that is just for this. You will find a couple of things that are going to be useful. You're going to find the Faraday constant. And you're going to find the definition of an amp. These really are conversion factors. They're relationships between 2 different units. This is going to be solved using dimensional analysis. And so we identify what are we starting with and what are we ending up with. Well, we're given 2 numbers, 12 grams and 3 amps. An amp is a coulomb per second. So this is the same as 3 coulombs per second. That could be a conversion factor, right? Because it can be hard to know, well, do I start with the 12 or do I start with the 3? 12 grams, there's no per in that. It's just a mass. That's what we're going to start with. So we're starting with 12 grams of silver. And then we identify what are we trying to find. What unit? Minutes. So we're trying to find minutes. Grams to minutes. Yeah, Google can't do that one for you. This is stoichiometry. What's in the middle of all stoichiometry problems? Moles to moles, right? So grams to moles to moles to grams. Anytime you've got a chemical reaction and you're looking at amounts of stuff, you might need this. So the moles to moles always happens. There's always moles in the middle. And the beginning and the ending unit can change. Here we are given grams, so we're starting with grams. So we'll go from grams of silver to moles of silver. And from moles of silver to moles of electrons. Because the electrons are in the current, right? Are we going to grams of electrons? No, we're not. We were given the current 3 coulombs per second. A number of coulombs is related to moles of electrons. So here we've got moles of electrons. Could we go from moles of electrons to coulombs? Yeah, we can just use the Faraday constant. So we can go from moles of electrons to coulombs. Both are a measure of charge. And then this allows us to convert from coulombs to seconds. And then I think we can convert from seconds to minutes. You want to figure out the path first before you start writing stuff down. So now we can write stuff down. 12 grams of silver. For each of these arrows, there's going to be a conversion factor. So from grams of silver to moles of silver, and grams of silver is going to go down here. We're just putting in all the units so the units cancel out. From moles of silver, we're going to moles of electrons. And so we'll put moles of silver down here. And then we're going to go to coulombs. And down here, moles of electrons. And then we're going to go to seconds. And coulombs is going to be down there. And then we're going to go to minutes. And seconds are down there. The key to the problem is figuring out this path. Once you do that, all you have to do is follow the path. There's very little thinking involved. You just follow this and write it out. See, the units here are the same as the units in the numerator. Grams of silver, moles of electrons, coulombs, seconds, minutes. That's the path we figured out. The unit in the denominator, we take the previous unit and we're going to divide by that so that those are going to cancel out and go away. So, we get here, moles of silver, what do I divide that by? Well, you divide it by this guy because we want the units to go away. We get all the units in place and then we put the numbers in. The units are going to tell us where to put the numbers. We don't have to think, well, am I supposed to multiply or divide? Put the number in with its correct unit. Let's start with this guy up here. This is coulombs and moles of electrons. The number is with coulombs. So down here, I have coulombs and moles of electrons. So I'm going to put the number with seconds and coulombs. Where's that relationship? It's right here. 3 coulombs for 1 second. So coulombs is in the denominator, so 3 goes down there with coulombs. And per how many seconds? Per 1 second. I'm just going to put the number with its unit. I don't have to think. Minutes and seconds, what's the relationship? 60 seconds is 1 minute, right? 60 seconds is 1 minute. Not, do I multiply by 60 or divide by 60? Over here, moles of electrons and moles of silver. That's going to come from the chemical equation. This is 1 to 1. Moles of silver to grams of silver. Yeah, look at the wall, periodic table, right? Silver, 107.9. 1 mole is 107.9 grams. It's the molar mass, it's the mass of 1 mole. And so now we just have to calculate. And just multiply by the top, divide by the bottom, and go all the way across. You don't have to write anything down. And just do it all in one fell swoop. I did something wrong. Let me try that again. That's better. And I should probably have 2 sig figs there, so we'll call it 60 dot minutes. This is stoichiometry with electrons. Here, we're not worried about cell potentials or anything like that. It's just stoichiometry. Any questions?